Hello friends, during last lecture we will talking about manufacture of ammonia by Haber process. After completion of manufacture of ammonia by Haber's process, today we will study the next inorganic heavy chemicals, that is sulfuric acid. So in our syllabus the point is manufacture of sulfuric acid by contact process. As we know, the sulfuric acid, it is an important inorganic heavy chemicals. It is also known as the king of chemicals. Why it is known as king of chemicals? Because it is used in the manufacture of fertilizers, coal tar products, metallurgical operations, industrial explosives, textiles, as well as plastics, acids, chemicals, cellulose, films, rayons, paints and pigments, as well as it is also used in the manufacture of dyes, drugs, leathers, etc. Therefore, sulfuric acid is known as king of chemicals. Here, manufacture of sulfuric acid mainly it is manufactured by two processes. The first process it is known as lead chamber process, while the second one it is called as the contact process. Nowadays most of the sulfuric acid is manufactured by the contact process. Now during this lecture we will study details of contact process. This process was developed by the scientist Phillips in 1831, which involves 4 steps. The first step, it is the preparation of sulfur dioxide by burning high grade sulfur or iron pyrites. The second step, it is oxidation of sulfur dioxide by air in presence of catalyst. Third step, it is formation of oleum, and fourth step, preparation of sulfuric acid. At first we will see this 4 step one by one. If we look at the first step, it is known as preparation of sulfur dioxide by burning high grade sulfur or iron pyrites. This is the reaction of the first step. Here sulfur it is reacts with air. Sulfur it is burns with air to form sulfur dioxide. Actually this is exothermic reaction. Here 70,920 calories heat is evolved, that means in kilojoule 296.7 kilojoule. Such a large amount of heat is evolved during this burning of sulfur in presence of air to form sulfur dioxide. Another one here, sulfur dioxide it is also prepared by using iron pyrites. The high grade iron pyrites is also burns with air to form Fe2O3 and the main product, that is sulfur dioxide. It is also exothermic reaction because a large amount of energy is evolved, that is in calories 82,340 while in kilojoule 344.5 kilojoule. The next step, it is an oxidation of sulfur dioxide. This is the most important step in the manufacture of sulfuric acid by contact process, that is oxidation of sulfur oxide by air in presence of catalyst to form sulfur dioxide. That is nothing but the conversion of SO2 to SO3. Here sulfur dioxide it is reacted with air in presence of catalyst to form sulfur trioxide. The reaction is twice SO2 plus O2 reversible equal to in presence of catalyst to form twice SO3, that is sulfur trioxide. Here this reaction it is reversible reaction, and also energy is evolved, that is in calories 45,000 while in kilojoules 188.3 kilojoule. The third step it is nothing but the formation of oleum by dissolving sulfur trioxide in 98% sulfuric acid. This is the third step for the manufacture of sulfuric acid by contact process. Here the reaction is SO3 is reacted with 98% sulfuric acid to form OLEM, that is H2S2O7. And the last step for the formation of sulfuric acid, it is the preparation of sulfuric acid of any desired concentration by diluting oleum with water. That means here in fourth step, oleum is diluted with water to form a desired strength sulfuric acid. The reaction is H2S2O7 plus H2O to form twice H2SO4, that is sulfuric acid. These are the main four steps in the manufacture of sulfuric acid by contact process. Now we will find out the physico-chemical principles, that is the technical conditions. What are the technical conditions to form manufacture of sulfuric acid by contact process? So here during the manufacture of sulfuric acid by contact process, here from among the above four steps, the second step, that is conversion of SO2 to SO3, or it is also nothing but the catalytic oxidation of sulfur dioxide to sulfur trioxide by atmospheric oxygen. This is the most important step in the manufacture of sulfuric acid by contact process. The yield of sulfuric acid by this process, it is entirely depends upon this conversion of SO2 to SO3, because this is a reversible reaction. That is twice SO2 plus O2 reversible equal to twice SO3, and in presence of this reaction it is carried out in presence of catalyst. This is an exothermic reaction, and this exothermic reaction heat evolved, it is 45,000 calories, or in Joule 188.3 kilojoule. It is a reversible reaction. Here the forward reaction is exothermic reaction, and it is associated with decrease in volume, that is 2 volume of SO2 plus 1 volume of O2, that means 3 volumes of reactants to give 2 volume of SO3, that is 3 volumes of reactants to give 2 volumes of products. That means this reaction twice SO2 plus O2 reversible equal to twice SO3. This is the most important reaction in the manufacture of sulfuric acid by contact process. By applying Le-Chatelier's principle to this reaction and obtaining favorable conditions, then and only then we get the high yield of sulfuric acid. So to obtain the high yield of sulfuric acid and to obtain favorable conditions, then and then we get the yield of sulfuric acid. So we can find out the technical conditions, that is one by one, and these technical conditions, that means first technical condition, it is nothing but effect of temperature. Here if we see this reaction twice SO2 plus O2 reversible equal to twice SO3, this is an reversible reaction. As well as if we see this reaction, here a large amount of heat is evolved, that means this is an exothermic reaction. Hence the equilibrium shifted towards the right with decrease in temperature, that is lower temperature favors the formation of SO3. However, the rate of reaction will obviously falls with decrease in temperature. That means if we decrease the temperature, then and then only we get the SO3, the product SO3 in large amount. That means 99.99%. However, if we lower the temperature, then the rate of reaction will obviously falls. Rate of reaction, it will decreases. So experimentally it is observed that at temperature 434 degree Celsius, that means 707 Kelvin, we get the 99% conversion of SO2 to SO3. So for this conversion of SO2 to SO3, that is by catalytic oxidation of SO2 to SO3, the optimum temperature to obtain maximum yield, it is about 425 to 450 degrees Celsius, that is in Kelvin 698 to 723 Kelvin. Even at this temperature, no doubt, even at this temperature, the reaction is uneconomically slow, and therefore to enhance the reaction velocity, a suitable catalyst is used. So if we see the catalyst, though low temperature favors the formation of sulfur trioxide, it slows the rate of reaction. As a result of it, to enhance the rate of reaction, a suitable catalyst is used in this catalytic oxidation of sulfur dioxide to sulfur trioxide. The commonly used catalysts are ferric oxide, finely divided platinum, and vanadium pentoxides. That means ferric oxide, finely divided platinum, as well as vanadium pentoxides, these are used as an catalyst. But here, if we look at these catalysts, here the best results are obtained by using platinum, but it is very expensive and also easily poisoned by impurities, and therefore nowadays the most suitable catalyst used, it is known as an vanadium pentoxides. So for the preparation of or conversion of or catalytic oxidation of sulfur dioxide to sulfur trioxide, vanadium pentoxide is preferred as catalyst, as it is quite efficient, cheap, and does not get easily poisoned. So this is the second technical condition, that is effect of catalyst. Then third one, that is called as effect of pressure. By applying law of mass action to the reaction twice SO2 plus O2 reversible equal to twice SO3, we get Kp, that is an equilibrium constant. So Kp is equal to partial pressure of SO3 raised to 2, that is P2 SO3 upon P2 SO2 into PO2. The forward reaction proceeds with decrease in volume. That means if we see the reaction here, 3 volumes of reactants giving 2 volumes of products, and according to Le-Chatelier's principle, here high pressure would give a better yield of sulfur trioxide. That means here if we apply high pressure in this reaction, we get the maximum yield of SO3, that is sulfur trioxide. But in actual practice it is not so. It seems that SO3 is strongly absorbed on the surface of catalyst at high pressure, and therefore incoming gases must have to diffuse through such layer. That means if we apply the high pressure when the reaction starts, that is SO2 and O2, these two incoming gases are diffused through such layer, and therefore this results in slow down the rate of conversion, and therefore here further the material of the plant get corroded. Hence here in this sulfuric acid, manufacture of sulfuric acid by contact process, the high pressure is found to be unnecessary, and therefore the process is carried out at atmospheric pressure, that is 1.5 to 1.7 atmospheric pressure, that is about in Pascal 1.515 into 10 raised to 5 to 1.717 into 10 raised to 5 Pascal unit. This is the third technical condition, that is physico-chemical principle, and last one, that is called as effect of concentration. If we apply the law of mass action to again twice SO2 plus O2 reversible equal to twice SO3, this reaction, the equilibrium constant that is Kc is equal to concentration of SO3 raised to 2 upon concentration of SO2 raised to 2 into concentration of O2. So it is evident that at high concentration of reacting gases favors high yield of SO3. That means if we increase the concentration of reacting gases, that is SO2 and O2, if we increase the concentration of SO2 and O2, then we get the high yield, that is concentration of SO3, or that is high yield of SO3. For this, SO2 and O2 gases are present in the molecular proportion of 2:3. Hence, amount of air to be mixed with SO2 should be carefully controlled. In practice, oxygen from Linde's plant or Claudi's liquid air plant is mixed with SO2 in the proportion of 3:1 by volume. So, concentration condition here, oxidation for the sulfur dioxide to sulfur trioxide, here the incoming gases SO2 and O2, here oxygen it is obtained from Linde's or Claudi's liquid air plant and it is mixed with SO2 in the proportion of 3:1 by volume. These are the four technical conditions. If we control these four technical conditions, that is physico-chemical principles, then the time of contact of the reacting gases with the catalyst must be carefully controlled and thus space velocity is adjusted. The space velocity, it is the number of cubic feet of the gas corrected to normal temperature pressure that pass over 1 cubic foot of the catalyst space per hour. That means the time of contact of the reacting gases with the catalyst must be carefully controlled and space velocity is adjusted. So, if we control the optimum conditions for the maximum yield of sulfur dioxide, that means here these optimum conditions are temperature of the reaction, catalytic oxidation of sulfur dioxide to sulfur trioxide, it is in between 425 to 450 degrees Celsius, that is 698 to 723 Kelvin. The pressure 1.5 to 1.7 atmospheric pressure and concentration of SO2 to SO2 gas in molecular proportion, that means the reacting gases, incoming gases SO2 and O2 in molecular proportions of 2:3. The catalyst, most preferably used catalyst, that is vanadium pentoxide or platinum, and the appreciable space velocity. If we control or if these optimum conditions are very useful to obtain maximum yield of sulfur trioxide. So during this lecture we discussed about the physico-chemical principles of manufacture of sulfuric acid by contact process. Thank you.